Okay, our next speaker is Trent McConaghy, and he has multi-dimensional skill set. He's also the founder and CTO of Solido Design Automation. So he's going to talk today about driving Moore's law with Python-powered machine learning.
Thank you. Hello, everyone. Thanks for the introduction. It's really a pleasure to be here. Normally, I present at machine learning conferences and circuit design conferences, so it's really cool to be at a conference on Python. Myself, I've been using Python since about 2001, and industrially since about 2002. So many years of Python. It's pretty cool to actually be in a conference surrounded by Python users. I'll get started. Very simple outline. I'm going to talk about Moore's law, and then I'm going to talk about how Python and machine learning help. So there's actually a lot of Moore's laws out there, or things sort of like Moore's law. So there's the Moore's law of brain scanning. And if you look, in 1973 or so, there was a resolution of about 3 millimeters. But as the years rolled on, as the years passed, the resolution went from 3 millimeters to 1 millimeter, and it just keeps going, all the way to, in about the year 2000, a resolution of about 0.1 millimeters. Now, the cool thing on this chart is the y-axis. It's a log scale, right? So what that means is it's an exponential decrease in the degree of resolution that people are getting. And that's pretty cool, right? With exponentials, very interesting things happen if you wait a while. There's a Moore's law for internet hosts. Going back to 1980, up till now and beyond, we've had this just explosion in the number of internet hosts out there. There's a Moore's law for DNA sequencing. So it was kind of plodding along. The cost of sequencing one human genome was pretty expensive back in 1965 or 1970. We couldn't do it. It was just too expensive, basically. But it kept producing, and starting in about 1995, that exponent changed, actually 1995, 2000, and it just got really crazy. It went from about 1.5x a year to about 10x a year. And that's cool, right? Exponentials can change due to different things happening. And I'm going to get to the answer of why this happened in just a couple of slides, but once again, there's sort of a Moore's law of DNA sequencing, and an exponential change in performance or price or something over time. So what is the real Moore's law anyway, right? Will the real Moore's law please stand up? So maybe it's transistors per chip. So we can look here. This is according to Intel processors. If you have a microprocessor from Intel, starting in 1971, the Intel 4004 chip had about 2,000 transistors, right? But then as time went on, by about 1980, with the 8086, it was about 20,000, right? And keep going. And by about 2006, the Itanium 2 had on the order of 1 billion processors. On the order of 1 billion transistors. These days, we're actually at about 2 billion, 5 billion, even 10 billion transistors per chip, which is pretty cool. But you know what? That actually isn't the real Moore's law. Maybe it's calculations per dollar. So maybe we can say, hey, for $1,000, how many flops can I do? Well, that has gotten a lot better over the years too, which is pretty cool. But that's not the real Moore's law either. Here's the actual Moore's law. It's about transistor size, which also therefore relates to density. And this is just the last several years and a few years going to the future. Of course, you could translate this all the way back to the 60s. And basically, in general, in a transistor, you've got a channel which electrons flow through. Think of it like a pipe, and you've got water coming in one side, water coming out the other. And the length of that channel has resistance. So if you have a longer pipe, then it takes longer for the water to get from one end to the other. So over time, the length of this pipe has been shortening. And in fact, it's become so useful to have this Moore's law happening that it's become a schedule. So the reference here is from the ITRS 2011 International Technology Roadmap for Semiconductors. So the $300 billion semiconductor industry actually sits down every year. There's about 300, 500 people who sit down and actually come up with a roadmap for the next year, for the next 5 years and 10 years, and to try to come up with ways to make sure that Moore's law doesn't end, and to make sure that this exponential keeps happening. So going back, actually, Moore's law is pretty cool because one of the phenomenons that happens is when silicon touches something, I like to think of it like a Midas touch. So in the case of DNA sequencing, what happened when the exponential changed from 1.5x to 10x a year, That's when DNA sequencing started to be used by machines instead of scientists in a lab playing with test tubes manually. Instead, it started going through these sequencing machines. And this was popularized by the likes of Craig Venter at Celera Genomics, and so on and so forth. So basically, and you see this over and over happening in all these different industries, and there's a lot other examples from biology especially that we're seeing in the last 10 years. And you might ask, well, what about Moore's law itself? How do we manage to get these computers to get smaller and smaller every year? It's about 2x every 18 months. Well, this is actually the silicon Midas touch applied to itself. Okay? So that means that you use the current generation of machines, of CPUs, of software, etc., to help design the next generation. If you think about it, it's sort of like the ultimate bootstrap. And then, of course, you have software tools sitting on top to help drive this, and this is computer-aided design software, CAD software. Moore's law is very much a powerful phenomenon. It's really a bull because, hinted by the silicon touching everything, writing this bull is what has enabled all these other advances. So starting at the bottom, we have these companies like Inphi, NXP, Scydance, and what they do is they build chips that go inside servers and racks of computers in general, and then that computing helps to drive the cloud. And inside the cloud, you have content from the likes of YouTube and Hulu and Netflix and all these things, and cloud computing, which helps to enable that. So that's one example, but there's other companies out there. There's companies like Broadcom, Avago, Huawei, and they drive communications infrastructure. And then, of course, we see a lot about the consumer side, where there's companies like Sony and Apple and Qualcomm, and they're designing a lot of chips for consumers. So your iPhones and your tablets and all this sort of stuff. This is driven by these guys. So we hear a lot about Apple especially. They are not only a computer company, they actually design computer chips. So, and that's really important. They've understood that it really matters for them. And Moore's law has enabled all these amazing things that we see, especially at the level of content and also at the level of consumer devices. There's a problem with Moore's law. There's actually always problems with Moore's law, and scientists try to figure out how to fix this, engineers, entrepreneurs, and so on. The problem right now is what I like to call variation gone wild. I had a picture for this, but my wife made me take it away. So let's just say variation went wild. Here's the problem. Transistors are shrinking, but atoms aren't. So as we started, you go back even 10 years, you were at 180 nanometers. Now we're at about 22 nanometers. So it's 22 nanometers going from this end of the channel to this end of the channel. The electrons flow from here to here, okay? So this is 10 years ago, this is now. So basically, you used to have Avogadro size counts for the number of atoms inside a transistor, 10 to the 23rd. But now we've got, in this sort of thing, 1,000, 10,000. And what this means then is, so in this channel here, when the electrons flow from here to here, this thing on top, this is called the gate. And it's only 1 or 2 atoms thick. This is the thing that controls how much electrons flow through. So twisting it up is sort of like twisting the faucet in your bathtub. As you twist the faucet, more and more and more, water comes out. So this thing is only 1 or 2 atoms thick. What that means is, imagine if you went to twist your faucet and it just suddenly triples how open your bathtub is. That's really a problem, right? You don't have very much control over the amount of water that's flowing through. And that, of course, can be very troublesome when you're trying to design a circuit that has supposed to be 1% precision, 5% precision, 10% even. Suddenly you're getting these 2x's of variation. And that's exactly the challenge that we see here. So if you have this variation in manufacturing, and this is actually statistical in a real physics sense. So when you're manufacturing a chip, there's these atoms that kind of float down and they lay themselves onto silicon, and it's very much put down in a random sense. And this is actually one of the things that enables large-scale manufacturing. It's what enables having 1 billion or 10 billion transistors on a chip. But the problem is this sort of process of doping that it's called, because it's random in a very physical, in a true physics sense, there's random dopant effects that cause this variation. It's variation at the device level, 1 transistor at a time. That propagates to variation at a circuit level, so with things like amplifiers and filters and bias generators. And that, therefore, translates from the device all the way to the circuit. And at the circuit level as well, you might have a microprocessor. If you manufacture 10 microprocessors, one might be 2 gigahertz and the other one might be 1 gigahertz, or even 0.1 gigahertz. So you have this giant variation in the performance of these things. And it can also happen in terms of power consumption. So you might buy a cell phone, and your buddy buys a cell phone, and your cell phone dies after 2 hours, and your buddy's like, hey, my cell phone doesn't die at all day long. And that actually can happen. So this is really a problem. It wasn't a problem 5 years ago or 10 years ago. It is now. So this is really a problem then. And the problem also is we want to keep Moore's law going. So we want to cut the size of the transistor by 2 every 18 months. This $300 billion industry relies on it, and all these advances in computing and cloud and so on also rely on it. So some of the sub-challenges are things like, you've got a memory with 1 billion bits. So you've got your 1 gigabit flash drive. How do you verify that? How do you make sure that every single one of those bits is sufficiently reliable such that you can ship it, so you can manufacture it, so that you don't lose money? How do you improve that design? How do you verify a PLL with 3,000 corners? So the idea here is a PLL, it's just another sort of circuit, just like an amplifier, okay? And you have to account for variation in it. You have to say it has to work when it's plus 50 degrees Celsius. You have to work when you're minus 20 degrees Celsius. You have to work if your power supply is 1.4 volts or if it's 0.8 volts. And all these other conditions too. It has to work when it's in sleep mode. It has to work when it's on mode, standby. And it used to be you might have, and you have to look at all the combinations of this. Okay, so it used to be you might have a couple powers and a couple temperatures. So you have like 4 corners total. But now, because of all these other challenges and variation, you might have 3,000. And the problem is to understand the variation in one circuit, to simulate with a circuit, it might take 10 minutes. So what used to take 10 minutes times 8, so 80 minutes to verify, now it takes 10 minutes times 3,000. So it just takes too long. So this is just an example of a problem. And all of this is all about getting lower power, lower delay, lower area, higher yield, all in less time. So there's a huge number of engineers out there in the world who are trying to actually address this. So just like there's engineers that design cars, mechanical engineers, what a lot of electrical engineers do, they work for Sony or Apple, for example. They go in every day to work, they sit down at their computer, they work with CAD tools to design computer chips, okay? And they're having real troubles. So with Moore's law, including variation, how might you address this? And the thing that my company hit upon back in 2004 when we were starting to found it was, let's use machine learning to abstract away the variation from the perspective of the designer. Okay? So the designers don't know about machine learning at all. They tend to know a lot about analysis with equations and Fourier transforms and a lot of other really amazing mathematical tools. But machine learning isn't among them. It definitely wasn't among them in 2004, and these days it's even less. So what we realized is, let's let the designer keep having his own flow, the flow that he's always had, and let's just hide all the challenges of variation under the hood, so that, and we use the tools for machine learning to do that. And by doing this, it helps designers to just keep going. And that's basically what my company does, Solido Design. We build machine learning powered CAD tools to help drive Moore's law. We're not the only company out there building CAD tools, of course. There's several companies in the world that do this, but really our specialty has been using machine learning, and it's really been a core strength. Other companies are starting to realize that, hey, these Solido guys are onto something, and we've seen a lot of others start to follow suit. But we've been pioneering this for the last 10 years. So let's talk about machine learning and Moore's law. And as I talked at the beginning, I've been using Python for a long time, my company as well. About 99% of the code base of my company is Python. Hundreds of thousands of lines of Python. We've been shipping it production since about 2005. So I'm also going to talk about how Python is being used to drive this machine learning, to drive Moore's law. And how I'm going to do it is just a series of examples. Some of them just a couple slides, some of them 5 slides, just to kind of give you guys a flavor of how all this code, all this machine learning code and all these ideas with Python might translate into real world use that actually end up inside the cell phones in everyone's pocket here, okay? So here's one example. On the left, what we have is a circuit. This is an OTA. It's a type of amplifier, basically. So in comes one signal, and out comes a signal that's 10x or 100x larger. And what you want is you want to say, hey, I'm a circuit designer. I'm used to working with these analytical equations. I'm used to sitting down and rearranging the equations to understand what variables depend on what in what ways. And traditionally, they would just use manual analysis to do this. But the problem is, with variation gone wild, those first order and second order equations get horribly inaccurate. They get off by 2x or 5x. But what if you could take silicon accurate data, so data that has been manufactured, information about the devices and so on, and pull that back into equations that the designers can look at and analyze and get insight into, okay? That's the idea here. So how it works is the following. You take the circuit, and you run it through something called SPICE. And SPICE is actually a tool that has been around since the 70s. It came out of Berkeley. In fact, it was arguably the first open source tool of the world. BSD is actually partly based on this, as well as the OS that came out of Berkeley around the same time. And so SPICE is a tool that takes a circuit as a description of a netlist. So just like we have HTML and XML and all these other protocols to specify things, there's also a protocol to specify a circuit. Each line basically says, here's a transistor, it's connecting from node 1 to node 2 to node 3. So you can take these descriptions of these circuits and you can actually simulate them. And this description of the circuit in text form can get converted basically into a set of nonlinear differential equations, and those simply get solved with off-the-shelf solvers that was pioneered by the people researching SPICE in the 70s. So, so what you can do is you can say, I'm going to come up with 100 or 1,000 different points in the space of this circuit design. So changing this resistance by, setting a resistance of 1K versus 10K, and another resistance and another capacitance. So you have a set of vectors, 1,000 different vectors. Each vector is a different design, and then you simulate each of those with SPICE. And what you get out is measures of things like gain and power consumption. And so then what you do, from the outcome of this, you basically have a set of X and Y, just like you would do normally in regression. But instead of just doing simply regression, you do something called symbolic modeling. So think of it like a white box regression. Instead of just spitting out a black box model that predicts stuff, you try to make that model white box so that you can actually look at it and as a human, interpret it. And that's what's going on here. So I'll get into the how, but that's the general idea. And what it can spit out is equations like this. So these are actual real results. Here, this is an equation for gain. Gain is minus 10.3 plus 7e to the minus 5 divided by ID1, that's drain current of transistor 1, plus 1.87 times ln of this equation here. And as you can see, there's a ratio here, VSG times VSG1 times VSG3, and so on and so forth. By the way, these equations are all to be within 10% accuracy. So in this case, the offset voltage, it turns out that it was 10% accurate simply by giving a constant. And it told you that, right? So if you say, I want to have 10% accurate solutions for each of my different performance measures, this is what it would spit out. This is super useful to an analog designer, a circuit designer who really deals with amplifiers and PLLs and these sorts of circuits. The initial way that we did this was a technique called genetic programming. So this is something that goes back to, actually, it was invented in the 80s, sort of in 2 or 3 different places, but popularized in the early 90s out of Stanford. And the idea is that you can represent a function as a tree. So for example, this function here, 4.8 times x3 plus square root of x2, the 4.8 times x3 is on this side, so these are combined via this operator. And then this subtree combines with the plus, with this subtree on this side. And in the end, we have this tree representing this equation, okay? And what you can do actually is you can actually search through that space of possible trees. So normally when you think about optimization, you're typically searching through a space of parameters, Euclidean space, or maybe it's discrete valued Euclidean, but it's not sort of a more generalized space. And you can search through more generalized space with things like genetic programming. It doesn't have to be genetic programming. You could use simulated annealing. You could use taboo search. There's a bunch of other off-the-shelf techniques as well. But genetic programming was really the one that really pushed this and pioneered it. So you search, and how you search the space with genetic programming, for example, is you initially randomly generate 100 or 1,000 of these trees, or 10,000. So just randomly generate these trees. And then you say, you evaluate them. So you see how much error does each tree have in predicting the output. And you say, okay, you know what? I'm going to keep the best half. I'm going to kill the worst half. And of those best half, each of them is going to get a child. So you create a child from the parent in one of many ways. I'll give an example in the next slide. And then you say, okay, now I've got these new children. I evaluate those guys. And I simply iterate. And after about 50 iterations, you can actually get pretty interesting trees. They can be pretty small. They can be pretty descriptive and pretty easy to understand. Here's an example of an operator where you start with a parent, or in this case, 2 parents. On the top here, this parent is one parent, and this is the other parent. It's called crossover. You basically can swap sub-expressions. So you're swapping the x times y in this expression with the x times x plus y sub-expression. And you can simply swap those in a computer science tree-based swapping sense. And then you have 2 children, and then you can evaluate those children. You can view this actually as interpolation in tree space. That's a cool way to think about it. And this is one example operator. There's actually a whole bunch of operators you can have. I guess I already talked about some of the example models with less than 10% error. So that's an example there. But overall, in my problem, I was really caring about circuit land here. I played a lot. I worked a lot with a lot of other machine learning technologies over the years. Going back to the mid-90s at National Defense with things like radial basis functions, feed-forward neural networks, all this sort of stuff. And so I had all these technologies that I'd worked with over the years. So off the shelf, I compared to them, right? So I compared the technology that I had built here, which I called caffeine. I do like coffee a lot, too much. To things like Gaussian process models, to support vector machines, feed-forward neural networks, boosted feed-forward neural networks, splines, quadratics, linears, constants. And in this particular set of benchmarks, this is 6 different problems, it actually had the lowest error in predicting unseen data. So I was pretty happy about that. It was not only a white box model, it was actually the lowest error in predicting. And I think part of it is that there was a bias towards reducing the complexity simply so that people could understand what was going on. And I think that helps a lot in general. If you have this bias to reduce complexity with the implicit aim to understand, it also has the side benefit of just being really good at predicting stuff. And overall, in Python terms, what's the stack here? It's actually 100% Python. Using Python 2.7, actually in that case, it was even an earlier Python, probably about Python 2.3 or so. NumPy and SciPy. Custom machine learning algorithm that I wrote was grammar-constrained genetic programming. It was multi-objective as well. And then I actually designed a grammar for functions. So I came up with basically a language to describe functions in a way that they're easy to interpret. And it's sort of the general idea of that grammar is sum of products of sum of products. I can give more details about all this if you guys want later. And then a third-party circuit simulator. Now, of course, you can use this off the shelf for anything else too, not just circuits, because it simply takes in an XY input-output mapping of data. Now, it turns out that that technology using genetic programming didn't scale so well. It was good up to about 20 variables. At first this was fine for us for the sort of circuits we were attacking, but then we started having customers saying, hey, I really want to see white box models for 100 variables, for 1,000, for 10,000, and these days even for 100,000 input variables. So I thought about it a lot, and I'd been following a lot of things in machine learning, but there was this whole idea, this trend in machine learning, starting in about 2002, and it's been going through till this day. What was driving it was image search and other search problems. The idea of, I like to call it BHALR, big, hairy, audacious linear regression, okay? And what it means is that normally when you think linear regression, you think least squares and all these, old school matrix approaches to do it like QR decomposition and whatnot. And that has certain constraints, right? You always, if you have 100 if you have 100 variables, then you need at least 101 training samples. But these new approaches, they don't need that because they use regularization. So that actually softens the problem. And they have iterative solvers. So you can actually get away, even if you have, if you have 100 input variables, you might only need 10 samples, and you can actually get something that's kind of sane, right? Because what they try to do implicitly is minimize the degree that you screw up your prediction afterwards. Mathematically, it's actually minimizing the volume of the confidence ellipsoid. But that's basically the sort of technology that I was following. And I realized you can build another technology around this, and it's dead simple. You take in your number of input variables, whether it's 13 or more, and you explode that out to 100,000 input variables, okay, by adding a whole bunch of basis functions. So the basis functions that I use are things like log and sine and cosine and x1 squared, x2 squared, 1 over x1 squared, all this, and also the interactions of those. So x1 times x2, x1 times sine of x2. And if you do it right, you can keep the computational complexity down such that it's linear in the number of samples and quadratic in the number of input variables total. So that's pretty cool. So it's quadratic in the number of initial input variables. And so that's the first step. The second step is you apply these BHALR algorithms, big, hairy, audacious linear regression algorithms to solve it. And on this elastic net formulation, which if you guys don't know, it's a really happy marriage between lasso and ridge regression. Lasso is a little too aggressive in pruning variables. Ridge regression is a little too non-aggressive. So elastic net is sort of the happy medium. And then when you're doing this pathwise learning, the pathwise part, it basically is tracking the complexity versus training error over time. So it starts off by saying, I have 0 coefficients, and I'm only using a constant, basically. And then I have 1 variable that kicks in to reduce my training error by a little bit, and then I have 2 coefficients that kick in to reduce my training error a little bit more, and you keep going until your training error stagnates. So you have this set of a trade-off between complexity, the number of variables that are non-zero, and the training error. So then what you can do is you can take that set and you can simply filter it on test error. So now you have a trade-off between complexity versus test error. And from there, you can say things like, I just want to have the lowest test error, or you want to have that whole set of models. Now, overall, though, there's a cool result here, and that is the scalability and the speed goes way up. So that's what it shows here. The technology that I showed you a couple slides ago was right here. This was the caffeine approach, the genetic programming approach. So to build a typical model, it would take about 10 minutes, and it would get a test error of about 4%, okay? This is the average across everything. Compare that to a linear model or a quadratic model, which have about a 15% error, and they take basically 0 seconds compared to this. The technology here, I call it FFX for fast function extraction. It takes also basically 0. I mean, 1 second, 2 seconds on this scale, it looks like 0. And it has actually a lower error yet compared to the caffeine. So I was pretty happy about that. And we actually use this off the shelf in several other technologies I'll show you later. We deploy this daily. This algorithm has been run in a black box fashion under the hood in some of our other technologies. It's probably been run 100,000 times now. And out there deployed in industry, it works, you trust it, you can consider it sort of a technology in that way. So the stack below this is, it's using, these days, Python 2.7 and NumPy. Scikit-learn, inside Scikit-learn, there's a whole bunch of different technologies for doing linear regression, including these BHALR approaches. So I'm using coordinate descent pathwise learning. So it's just a particular formulation. And yeah, and it's the elastic net formulation problem to solve. And inside there, it's this FFX tool. So FFX wraps the scikit-learn to explode the number of basis functions, to do the non-dominated filtering, et cetera. Of course, this is general enough for other domains. We have an extension for classification. Of course, you can just put a logistic map on top of this. And actually, we've open sourced this too. So if you want to play with it, use it. It's out on there online at trent.st/ffx. And some of my friends have used this. I've never promoted this really heavily, but feel free and use it. Yeah, go for it. I'm going to keep going, though, and I'm going to talk about several other technologies that we've been using to help drive Moore's Law using Python-powered machine learning. Here's one. So here, the challenge here is, let's say you want to just understand the distribution of power consumption. So you manufacture 1,000 chips, and you want to know, okay, what's the average power consumption? What's the, for the top 5%, what's the 95th percentile power consumption? And so on and so forth. So that's up here. Imagine here we've manufactured, this looks like about 1,000 samples. And this would be a density fit on top of it. Now, you can also transform this density fit. In here, the y-axis is the actual density. But it turns out when you have a long tail, it's kind of hard to look at because it's hard to distinguish what the density is here versus the density here. But it really matters, actually, for a lot of problems. You really want to know whether you're 99.5% versus 99.6%. So it turns out there's a visualization to help you see that. It's called NQ. So you take this y-axis, so every single sample here, the fit, and you just transform it via an exponential transform, which is actually the Gaussian formula, the normal formula. And you have this value here. So this is normal quantile instead of probability density. So you take the probability density, you convert it to a CDF first, a cumulative density, then you transform it to via this exponential, and you now have a different y-axis. This is really cool because now I can distinguish this part of the tail from this part of the tail, okay? That's super useful. You can distinguish 99.1% compared to 99.2%. And that really matters when you're comparing 99.99% versus 99.999%, much higher yields, if you will. So the challenges that we had was, if you fit a model on here, a density model, you can use something like KDE, kernel density estimation, right? And what you would do with KDE is you just have a tiny little Gaussian on top of each of these points, okay? And it estimates what the sigma for that Gaussian is based on the overall spread, number of points, that sort of thing. The challenge is with that, the tails drop off really quickly. So if you convert it to this normal quantile plot, what you would have is you would have this curve that would look like this here, but then as soon as you get here, it would just drop off and go to basically like essentially zero density. And that's really a problem because it extrapolates really badly. And what we wanted, what our engineers wanted, our users designing computer chips, they were wanting to say, hey, I've done all these samples, and this gives me, tells me about yield of 3 sigma, so that's 99.7% yield. They want to know what's going on at, say, 4 sigma, which is 99.99% yield. So it's a failure rate of 1 in 10,000 versus 1 in 1,000, or 1 in 10 million, okay? And so the KDE, something off the shelf like KDE that's non-parametric, just simply failed. What we did, we simply built many density models, so dead simple. We looked at a whole bunch of fancy approaches. In the end, We just build a Gaussian, a mixture of 2 Gaussians, a mixture of 3 Gaussians, 4 Gaussians, 5 and 6, and so on too. A log normal, a uniform, a Rayleigh distribution, KDE is a backup, and even a few more. And then we picked the model with the best fit. But it couldn't be just the best fit according to MLE. MLE is really caring about densities in this space. What we really cared about was being able to extrapolate in an insane way. So basically we did a least squares fit in NQ space. That was our way of measuring the goodness, okay? So in the end, a deadly simple algorithm, but this works and scales in a really beautiful way. So engineers like that. What's the stack? Python 2.7 NumPy. We use some SciPy stuff. So SciPy has kernel density estimation, and it's got quite a lot of optimized functions. So we use the BFGS one, which is a second order Hessian approach that's really nice, really fast. And some other specific distributions too, like the Weibull and the Rayleigh and stuff. And then the custom ML algorithm is simply a conversion to and from NQ space. And the special case distributions, things like we wanted to fit sometimes to a uniform, right? So that's that. Then finally, a third-party circuit simulator. In our case, we tie into these SPICE simulators that other companies provide. So in general, though, it's pretty simple, right? And that's part of the point. Now, I kind of touched on it when I was back here. I said, when you want to go from 3 sigma to 4 sigma, and you want to simply extrapolate, that's cool. But what if you actually can't safely extrapolate? What if things really change once you get farther out in that space? And this can really happen, right? Let's say you have some sort of digital circuit where it just simply accidentally shuts off once you get, say, at 3.5 sigma. Once you get into a region of your input space where just things fall off a cliff, right? So no amount of extrapolation will help you. So what you really need is you need actually good data out here. But to get good data out here, basically to go from 3 sigma to 4 sigma, you're going from 1,000 samples to about 1 million samples. To go to 5 or 6 sigma, to go to 6 sigma, you need about 1 billion or 10 billion samples, okay? So 10 billion samples, the problem with that is that you'd have to do 10 billion simulations, and that would take you about 2 months on 100 cores, right? And that's a problem, of course, because these companies, they design chips where they have these cycles of every 3 months or 6 months. You can't consume 80% of your cycle by just waiting for one design to verify, right? You've got to ship that iPhone yesterday, right? So it's a very, very competitive industry, and time really matters. So what you need to do is you need to somehow get your samples. If this is the plus or minus 3 sigma that 1,000 samples will get, you need samples out here, okay? So 5 sigma, 6 sigma. And you need to do it in 10 minutes or an hour. So there's quite a few different approaches out there in the literature to do this, going back even to the 50s. So in the general class of Monte Carlo algorithms, there's some subclasses called importance sampling. The idea there is to simply distort the distribution to have samples out in the tail. It turns out that importance sampling doesn't scale very well. It works for 10 variables or maybe 50 variables, but a lot of our problems have 10,000 variables. And it has actually exponential increase in variance with the number of dimensions. So it's very unhappy when you get to 10,000 variables. So what we needed was we needed something that worked, that had properties more like plain Monte Carlo itself, pseudo-random sampling, drawing from the true distribution, which actually doesn't care about the number of dimensions. That's a really cool magic trick about Monte Carlo, right? If you look at the formula for Monte Carlo, its accuracy is only dependent on the number of samples, right? So that's a really cool property. So we said, okay, let's use that as a baseline. So let's draw 10 billion Monte Carlo samples, and let's simply figure out which of those 10 billion should we simulate. And the way that we figure that out is doing a very simple pilot run to start with of about 100 or 500 or 1,000 simulations. We build a model from that, and then we use that model to predict which samples might be out at the tails. Okay, so we do 1,000 simulations to build a model, and then we do another 1,000. Then from that model of 10 billion points, we do another 1,000 simulations that we predicted which we think are the best. And even if the model isn't that great, we pick the 10 best, the 10 that are the most extreme values, right here, and we show those. So you can liken this actually to sort of like a web search, Google search. And in fact, the shape of the problem is very similar. We've got 10,000 input variables. We've got about 10 billion points. In web, they start with, say, 40 billion web pages. They chop it down to 5 billion using heuristics. And then they sort it, they rank it. So we've got similar. And then just like you're viewing on a web page, the first set of 10 links from Google, we're showing the top 10 results right here. We have ways actually to fill in the rest too, the rest of the PDF. But just focusing on the top 10 is what matters the most. So, and the result is you can run this for 20 minutes on 10 cores, or even 20 minutes on a laptop these days, right? So that's a lot better than 2 months and 100 or 1,000 cores. And people are pretty happy about this. This has actually been adopted by the majority of memory designers in the world. So if you have anything that uses memory, it's probably used this under the hood. We've been shipping this for about 4 years now. So the summary, the stack under that is it's using Python 2.7, NumPy, SciPy. It's using scikit-learn pathwise learning because it's using this FFX algorithm, this regression algorithm I mentioned a few slides ago. It also has 1% C. And the reason is when we're sorting those 10 billion points, it's too slow to do it in pure Python. And we actually looked at a whole bunch of the different accelerators, things like Blaze and this sort of stuff. But in the end, we went straight for C. So we're using C in two things. We generate the random numbers using Mersenne Twister, which is actually the default in Python these days. It didn't used to be, but it is these days. And for each of those points, after we generate it, we simulate the regressor, the FFX regressor, in C. And incidentally, you actually need something like Mersenne Twister. It has a period of 10 to the 19. LCG, these linear concurrential generators, they only have a period of about 10 to the 12, 10 to the 13. And if you think about it, if we're looking at 10 billion points, that's 10 to the 10, right? Times 10,000 variables, that's 10 to the 4. So we're already at 10 to the 14 right there. So 10 to the 14 is big, it's beyond what a regular random number generator can do. So I was actually kind of surprised by this, right? I've never ever thought that something like LCG could conk out, but it actually literally does in our case. But Mersenne Twister we use. So that's basically the stack that we have for this tool for rare event estimation. Here's another problem that's kind of interesting. It's the idea also of searching through structures. So rather than searching through a space of a Euclidean space, or maybe a discretized Euclidean space, what you're trying to do is actually you're trying to come up with, in this case, analog circuit topologies. So a circuit topology basically is a device like this transistor here, connected to this transistor, connected to this in certain ways, right? And so you can view it as a graph. You can view it in other ways too. You can actually frame this as a tree if you like as well. And actually that's how I did it here. So I actually came up with a language for circuits, a grammar for circuits. And then what I did was I actually went through the 3 or 4 major analog design textbooks, and I populated this language with every circuit in all these analog design textbooks. So then in the end, I had a language for analog circuits, and I used genetic programming once again to search through this language to come up with optimal topologies. So what the results are here, this is an example of, an example of a trade-off between gain bandwidth, so gain and bandwidth and power of a circuit. And so in this case, along here, every single one of these points is actually a size topology. In this case, it's this topology, but each one of these points along here is just this topology with different sizings. But once it gets to a certain point, in this case about 1.8 gigahertz of gain bandwidth, it needs to switch to a different topology. And you can see it goes from here to here, and it's a more complex topology. It's got this second path, and that path actually doubles the power consumption. So you can see here, this is power consumption on the y-axis, right? So in order to get a gain bandwidth beyond a certain point, you need to switch to a different topology. That is super useful for analog designers to know, okay? It's really, really cool knowledge. This is also cool because it is directly tied to the silicon information itself. So you run this once at the most modern process node. These days, that's 14 or 16 nanometers. And then you have this information, and you're good to go. All right, the stack is similar to the other ones. It's grammar-constrained genetic programming. It's also got a derivative-free optimizer that we rolled, and a high-resolution interpolator, just for some of this. This is also open source at trent.st/mojito. That's my second favorite drink. It's my wife's favorite, actually, but it's my second favorite. I guess I'm running out of time, but I talked about this problem of of corner analysis, and the idea there is you've got these 3,000 corners, but you only have time to do 100 simulations. How do you verify across those 3,000 corners? You can cast this as a global optimization problem, and then you can solve it that way, and you have to make sure that the global optimizer solves in a very, very reliable fashion. And so we used what we call model building optimization. Other people call it sequential model building optimization or Bayesian optimization. And that's how we kind of approach it. Here's a screenshot from the tool. And then we solve it in a reliable fashion. And in this case, to solve this problem of 3,000 corners, we can solve it in 275 simulations, okay? So designers really like that. Some of our customers use this for every single circuit that they ship. So every single custom circuit, the likes of NVIDIA, Qualcomm, these sorts of companies, every single circuit that comes out of them runs through this tool, okay? So I don't have time to go into detail. Under the hood, for the model building, it's using Gaussian process models. which also very happily is part of scikit-learn. We used to have to roll our own, but we are very happy that scikit-learn has that. It turns out that it doesn't quite scale beyond about 1,000 samples, so we had to have a divide and conquer approach to take it farther. And so the divide and conquer approach is basically a cart model that wraps a Gaussian process model. Okay, so cart at the top level, Gaussian process models at the lowest level. So Gaussian process models when you're for every 700 samples, never more than 700 training samples. And that actually gives it an overall O to the n log n learning, because now you have O to the 1 learning on the Gaussian process models. Gaussian process models traditionally are O to the n cubed in the number of training points. So that was actually a huge benefit for us. We went from O to the n cubed to O to the n log n, right? And that made a big difference for our customers because they were starting to attack these larger problems where they needed to have 10,000 training points or even more. And it turns out that this thing benchmarks really well. You know, places like 10x faster, 100x faster, places where plain Gaussian process models completely failed, we could solve, and it even had lower error. So we were happy about that. Here's another very quick thing. If you're trying to do just simple random sampling, maybe Mersenne twistor or something else, if you're doing random sampling in a 2D uniformly distributed space, some of those samples could clump together, or maybe they have big gaps, right? So if you're trying to estimate, say, the mean or the standard deviation, that actually increases the variance of those estimates. It turns out that there's technology like lattice rules and other low discrepancy sampling approaches that give you a perfectly spread set of samples, okay? What that does then is it means you can have a lower variance estimate of mean and standard deviation and so on. Lattice rules is actually among the best because it actually can scale up to 1,000, 10,000 plus variables. Other approaches, things like Latin hypercube or digital nets or Halton, these sorts of things, they actually have issues like scalability or only not considering variable interactions. And this gives speedups. You know, here's one set of benchmarks. Here's a good example of the variance reduction. So this is plain pseudo-random sampling versus the lower variance. So this is the number of samples in log scale. This is the average error in estimating mean. And you can see, for example, if you want to estimate mean within 2% accuracy, it needs 10x fewer samples. And actually, as you want to get lower accuracy, you get even bigger speedups. So if you want to get within, say, 0.1% accuracy, you've got a 1,000x speedup. So this is pretty cool, right? So if you're using random sampling and you want to get a 2x or 100x for free, use lattice rules. And you know, we have a lot of benchmarks on this. And also, you know, we use in this case we have another tool that's it's like optimization, but it's a really beautiful interface, so you can explore and slice and dice the space. It's sort of like the technology stack of before, except we've got Qt4 and Chaco. So these are Chaco plots. Inside my company, inside Toledo, we actually have overall we have 6 different products. And each of these products has a giant list of different machine learning tools that we use. I know that it's a pretty small font there, but to give it a feel, on the top left, we've got regression and interpolation with confidence intervals. We've got model-based optimization. In the middle, we've got low discrepancy sampling, 1D density estimation, and so on and so forth. So a lot of machine learning in a whole bunch of different ways. As far as our customers are concerned, as far as our users are concerned, they've got this really beautiful interface that just works. They don't have to think about the machine learning. They don't have to think about the code. They're just using a tool, something like this, okay? So in conclusion, you've seen a talk now on how Python and machine learning are literally helping to drive Moore's law. It's the Silicon Midas touch applied to itself. And if you've got a cell phone in your pocket, that Python, that machine learning, almost certainly had a hand in designing that phone. And the servers in the cloud, all of these chips. And that's all. Thank you very much.
That was very impressive. Does anyone have any questions?
You said you were working with multi-objective optimization. How many objectives and what sort of properties do they have?
Yeah, so we mostly worked with multi-objective in 2 places in, let's see here. In this problem, in the white box modeling, in this case, it was 2 objectives. So minimizing prediction error on unseen data and minimizing complexity. In other cases, in this particular problem right here, here we have 2 objectives, but in this case, there's actually up to 8 objectives.
Okay.
And that problem changes dramatically because the volume of the surface, or the hyper area of the surface that you're trying to cover, grows exponentially. And if you use the wrong multi-objective search, it's going to spend all its time searching the corners. So something like NSGA2 will completely fail. And what we did here was we used a variant of, what's it called? Well, it's another multi-objective variant, like a multi-objective evolutionary algorithm that spent more time on the knee. So basically more towards the center of the trade-off. It also spent some time along the edges, but we focused it more towards the center. And so that made it possible.
Okay, cool.
Okay, and I guess one other thing related to that too, we also have constraints on this. So I said constrained multi-objective search. So you might say, you know what, you never need power consumption beyond 50 milliwatts. And if you can chop that out immediately, it means that it's not spending any effort really searching that space once you've met your constraints. Okay?
Thank you. Okay, so it looks like there is no other question. If you have any questions, feel free to ask them offline. And we break for lunch now. Thank you once more.